Here we're going to discuss what's called the amplitude. We're going to see reflections and vertical shifts of trig functions. So I've graphed a function here that is a wave. It looks a lot like sine that we've seen before, but there are a couple of important differences. First of all, it looks like the entire wave has been sort of shifted up 1 unit, right? Basic sine used to start at 0 and go like this, okay? But now it's no longer starting at 0, it's starting at 1. So the amount that the function has been shifted up or down, we refer to that as a vertical shift. So in this case, there's been a vertical shift up 1 unit. Let's write that down. That's just showing you that the whole thing's been moved up 1 unit. So we've seen a vertical shift, and we'll call that up 1 unit. Okay? So you can kind of see that the whole graph's been sort of pushed up 1. But there's another change, right? Not only has the entire graph moved up 1, it looks like the wave is of larger, what we call amplitude than we had before. Amplitude measures the height of the wave. Now the height of the wave is always measured in relationship to the base level. The base level would be where the zeros used to be. So this would be considered the base level. So the amplitude of this trig function, of this wave, if you will, would be, well, let's see, 1, 2 units, right? So this is called the amplitude. And it's equal to 2 in this case. Notice that the amplitude is not all the way from the top to the bottom. It's only top to midway, the midpoint, the reference level, which used to be 0. So you go from where it used to be 0 all the way to the new top, just half of it basically, half of the entire thing. And in this case it's 2. And we refer to that as the amplitude. Okay, now it turns out trig functions can have also what are called reflections. Now the reflections that we're going to be dealing with are going to be reflections across the x-axis. And it's important to realize that reflections and vertical shifts, those can interact, and the order of these matters. And so let's see some examples to see how these relate to each other. So we're going to find the amplitude, any reflections and vertical shifts, and then graph this function, y equals -3 times sine x minus 2. Okay, so the first thing I notice, or the first thing that we want to notice, is that it's no longer just y equals sine x, right? We have a couple numbers in here that have some geometric meaning. First of all, the amplitude. You can always find the amplitude by taking the absolute value of the number being multiplied by sine or cosine or whatever you're looking at. So -3 is being multiplied by sine, so I take the absolute value of -3, which is 3, and that gives me the wave height from the average, right? From that 0 place like we saw in the previous example. Now it's important to notice that amplitude is always positive, right? It's the height of a wave, and the height is always a positive number. The second thing I notice is that we're going to take -3 sine x, and then finally at the very end we're going to subtract 2. This little subtract 2 is responsible for the vertical shift. So the vertical shift is going to be 2, but downward because it's subtraction. So it's going to be, let's write, down 2. Okay, and if that was positive right there, it would have been up 2. So it's a vertical shift down 2. Now, the way you apply these transformations, the order matters. Oh, by the way, there's one more transformation here, and it has to do with this negative sign here. So notice how the amplitude is just the absolute value of this number. If the number is negative, that's responsible for a reflection across the x-axis. So let's write that down, that there's also a reflection across the x-axis. Okay? Now the way we're going to graph functions is as follows. We're first going to focus on the argument of the function. Now the argument is whatever in this case I'm taking sine of. So this is sine of x. It's not sine of x minus 2, it's just plain old sine of x right here. So now in this case it hasn't been changed, right? It's not like x plus pi or 2x minus pi over 2 or anything like that. It's just x. Now when it's just x, that tells you that you neither have you don't have any translations horizontally. You don't have a horizontal translation left or right, nor do you have a period change. What that means is that this function, this function we're going to graph, that we're going to start at 0 and we're going to end at 2 pi. But the way it's going to look, in a future example, it'll be nice to have this written down here. You simply take the argument, in this case just plain old x, so this is a little boring, but we'll see it be more exciting in the next example. You simply take that argument and you set it to where sine used to start. Well, sine always starts at 0, and where sine used to end at 2 pi. Okay, and once you do that, you solve the resulting equations for x. Now, like I mentioned, these already have x by themselves, and so they don't give us anything exciting. But what you do is then you take that interval and you take the right endpoint and subtract the left. So it's 2 pi, take away 0, and then divide by 4. And what you get in this case is, let's see, 2 pi divided by 4 is pi over 2. This is what I'm going to refer to as, in the next example, as a step size. So step size. So what you do is you start at the left, and that's your first left point when graphing on the x-axis. Okay, so the first one would be 0 in this case. And you step in this far. You do that 4 times. So I get pi over 2. This is my next important point. Step in another pi over 2, brings me to pi. Step in another pi over 2, 3 pi over 2. And then finally 2 pi. And after I stepped in 4 times, you should end at 2 pi. Okay, that's a pattern we're going to see. Once you've determined what happens on the x-axis, now it's time to talk about what happens on the y-axis. And this is where the amplitude, the reflection, and the vertical shift are all going to play important roles. So here's what we do. We remember the basic graph of sine, right? The basic graph of sine was this. It started at 0, and it went up to 1, came down to 0, to -1, and then back to 0. Okay? So this was 0 before for y. This was positive 1 for y. This was, of course, 0 again. This was -1 for y, and this was 0. And what we're going to do is we're going to take those 5 points, 1, 2, 3, 4, 5, and look at how they've been transformed. So the idea is that, let's start with 0. The idea is that 0 used to be the output of just sine x, right? That used to be the old y coordinate. But now you're taking that y coordinate, that 0, and you're multiplying it by this number and then subtracting 2. Let's write that down here. We're taking -3 and we're multiplying it by the old y coordinate of 0, and then we're subtracting 2. Well, what do we get? Well, -3 times 0 is 0. Take away 2 is -2. Okay? That tells you where the new y coordinate is. So at this first significant point that we already found, right? 1, 2, 3, 4, 5. At the first significant point, the x coordinate is 0, but the y coordinate, which is what we're determining now, is -2. So 0 for x and y with -2. This is the first point on my graph. Okay? These were just places to line up for the x coordinate. Then we found out the y coordinate, and then we put those two things together to get a point. Okay, 0, -2. Let's go on to the next one. The x coordinate's pi over 2. What's the y coordinate? Now, it's important to note, I'm not plugging in pi over 2. What I'm doing is I'm saying to myself, oh, the y coordinate, the old y coordinate used to be 1. I'm plugging that 1 in right there. Not for x, but I'm replacing sine x with 1. So it looks like this, -3 times 1, right, minus 2, and I get -5. So here I get, for this value of x, I get an output of -5. There's my second point, like so. Okay? Go on to the next one. I used to get 0. Well, I already know what happens to 0, right? It's the same thing that happened to this point, but I can write it. So -3 times 0 minus 2. That gives me -2 again, right? So at this point, I get -2 again. So it's right there. And then I go on to the next one, right? And at the fourth point, let's see, 1, 2, 3, 4. I used to get -1. So I plug -1 in again, and I get -3 times -1 minus 2 is +3, right? Minus 2, which is 1. So at this fourth point, I get 1. Okay, and then finally, our last one would be back to 0. And we know what happens at 0. So it's negative 3 times 0 minus 2 is equal to negative 2. And at this value, we're back to negative 2. And then what I do is I plot the wave based upon 1, 2, 3, 4, these 5 significant points, okay? So I can see that the wave is going to look like this. This is going to be the graph of my function, okay? Let's go ahead and graph that now. And that would be the graph of my function. So notice that let's look at these transformations. The amplitude is 3. Here's the baseline, right? And the amplitude is the height of the wave from the baseline. So I can see if the baseline's here, right, the peak of the wave is 3 units away from that baseline. Or you can go 3 units up either way, right? But either way, the amplitude is a positive 3. Notice there's also a vertical shift 2 downward, right? No longer is the 0 at negative 2. The 0 is at, sorry, no longer is the original point at 0. The original point's at negative 2. And finally, there's been a reflection across the x-axis. Basic sign looked like this, but if you reflect it, all of a sudden the graph looks something like that. Okay, it's been inverted, and that's what happens here. You can see how the graph looked like that. Now you have to be really careful. I didn't simply apply these reflections in this order. What I did was I used this method here. I first found the corresponding points on the x-axis, and then I used what are called the 5 significant points. 5 significant points. And you have to know the original 5 points, right? The original y coordinates, and you plug them in the way I did here. And I used that to get 5 more points, and then I traced in the curve. I did not graph this using transformations, even though I identified what transformations do exist in this. And you could use this as a check on this, but you have to be a little bit careful with transformations because you have to really know how to apply them. In this case, the way you would apply them as follows, is you'd start with basic sine, and then what you do is you would change the amplitude. So you'd start with sine, and then the amplitude would go up 3, so like that. And then you'd reflect it with the negative there. So you'd reflect that graph. So instead of going up like that, right, the whole thing would be reflected, so it looked like this. And then finally you'd move that down 2 units to get what I just graphed. So we're not going to be doing much with graphing using transformations. We're going to graph using the 5 significant point method. Okay, let's try another one like that. Let's graph y equals negative 2 times cosine of pi over 3 times x plus 3. Okay, so as I mentioned, the first thing we do is we identify what we have, our transformations. So our amplitude is going to be the absolute value of negative 2, which is 2. And our, actually we have a period change, right? Because x is being multiplied by something. So our period is going to be 2 pi, that is the old period of cosine, which was 2 pi, divided by that number, pi over 3. That's how you find the new period. And then when you do that, the pi's are going to cancel, and you're just going to get 6. Finally notice now that there's a reflection because of the negative here. There's a reflection across the x-axis. And then finally there is a vertical shift up 3 units. So it's the vertical shift up 3 units. Okay? So now that we have an idea of what to expect, let's go ahead and graph the way we talked about graphing a moment ago. That is, you set the argument, in this case pi over 3 times x. You first set it to where cosine used to start, which was at 0 on the x-axis. And then you set it equal to where cosine used to end on the x-axis, which is 2 pi. Okay, then you solve both of these equations for x. So I'm going to multiply both sides by 3. I'm going to clear fractions. So I'm going to get, let's see, it's going to be pi times x is equal to 0. And then finally divide both sides by pi. So I'm looking at, it's going to be x is equal to 0. So notice that the function still starts at 0, and that's because there's not a horizontal translation. We'll see those in future videos. Those are called phase shifts in future videos. Okay, here we'll multiply both sides by 3 again. And the 3's cancel. And you get pi times x is equal to 6 pi. And let's now divide both sides by pi. and I get x is equal to 6. Okay, so the graph starts at 0 on the x-axis and ends at 6. Now, as I mentioned, you take the end, which is 6, subtract the 0, which is the beginning point, and then divide by 4. And this gives you your step size. So in this case, my step size is 3 over 2. All right, so now we're going to start at 0 and step in 3/2 each time. So it'll be 0. Okay. Now, if you do that, you're going to get, let's see, 3/2, right? Next one's going to be another 3/2, so 6/2, 9/2, 12/2, 15/2. Let's see, that's not quite right. Let me try this again. So the mistake I made, everything is right. It's just the x-axis is too compressed, right? So the problem is that I'm supposed to end at 12/2, which is 6, but it's so tight in here that it's not. I didn't really scale this properly. Let me go ahead and redraw this graph here, and you can see the scaling, right? You want to make sure that you have enough space, and my original graph didn't have that. So this is actually a nice thing for you to see. So let's rescale that. Okay, so x-axis and y-axis. All right, so we're starting at 0, right? So let's step in once and we get 3/2. Step in again and you get 6/2. Okay, and then you get 9/2. And finally you get 12/2. Now after you stepped in 4 times, right? 1, 2, 3, 4, you should end at 6, and that's the end point. And that's a check on your work, right? Step in 4 times and you should end up at your final endpoint. Now, as far as the y-axis is concerned, I'm going to scale that as well. And I'm going to see basically what's going to happen. At some stage, the cosine is going to be a -1, and -1 times -2 is going to be +2, and that'll bring me to 5. And that's as high as it's going to go. So scaling the y-axis, I'm just going to go 1, 2, 3, 4, 5. Again, being aware of what's coming. So this is how we go about scaling axes. And then let's go just -1 on the y-axis. Okay, so remember the underlying graph is cosine, right? So what does that underlying graph look like? Well, it starts at 1 actually, right? And it comes down and it goes back up like so. So the y-coordinate here is 1. Here it's 0. Here it's -1. Then back to 0, and then it ends again at 1, okay? And as we mentioned a moment ago, that's important because we're going to go through the 5 significant points starting with these values of y. Give myself a little bit of space right here. Okay, so imagine y came out of here. You take that y of +1, right? So imagine 1 came out of this. 1 times -2, let's write that here. So it's going to be -2 times 1 plus 3, and that's equal to +1, okay? So my first value happens to still be +1. Okay, now originally it was +1, just so happened it's +1 now as well. Okay, next one, 0, plug that in. -2 times 0 plus 3 is equal to 3. So at the second significant point, right, which is for this value on the x-axis, I go all the way up to 3, like so. So it has that value for x and this and 3 for y. Next one would be -1, plug that in, so it's -2 times -1 plus 3. Notice I'm not plugging this in for x. I'm replacing cosine of all of that with the -1. And when I do that, I get 5. So at the third significant point, I'm all the way up to 5, like maybe right about there. Okay, and then back down to what I used to get for 0, which was right here. So that would be -2 times 0 plus 3, which was 3. And then finally, we're back to +1. Plug it in. So it's going to be -2 times 1 plus 3, which is 1. And we're back down to 1 over here. Okay? And so then you have 5 significant points. Boom, 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 boom. And you want to draw a curve through those, right? Remember, it's cosine. So let's go ahead and do that now. Okay, and there's my graph. Notice that this would be the reference level. The amplitude, of course, is 2, right? all the way up to the 5 from the reference level. And notice that it doesn't look like that. It looks like it's been inverted, right? It's sort of upside down, and that's because of the reflection across the x-axis. The period has been changed. No longer is the period 2 pi. The period is 6. You have to go 6 to get repetition in the cycle, or to complete a cycle. And notice that, of course, the graph has been shifted up as well. No longer is it centered around 0. It's centered around 3, and that's because the vertical shift has been up 3. All right. Okay, let's go ahead and just talk about how to graph this function if you were to use transformations. Let's look at that now. So to graph that same function using transformations, what you do is you start with the base function, which in this case would be cosine, and build up using transformations. So you'd first graph this, y equals cosine. Okay, and we're not going to do that here, but I just wanted to guide you through how to do it. And then what you do is you would first get your period change. So y is equal to cosine of pi over 3 times x, and that would be changing the period. And then what you do is you multiply that by -2. So -2 times cosine of pi over 3 times x. So basically you graph this first function, graph the second one with a period change, and then you take that graph, multiply it by -2, and that changes, for this graph, it changes the amplitude, and it also introduces a reflection. And then what you'd finally do is take that graph right there, and you'd finally add 3, which would be your vertical translation. Okay, so this would be a vertical shift. Now it's important to go in this order, and the order I chose was whatever order it took for me, or the order that I could use to get back to the function I'm trying to graph, starting with the base function of cosine. Okay, so you'd graph these 4 in order, applying those transformations, and you'd have your final function. Like I mentioned, we're going to be using the 5 significant point method. I think that's a better method because it's easy to get confused with the order of transformations. But either way, they're both good ways. Okay, until next time.